This one. Perfect. Thank you. Okay, we have time. Good. Does this work? Good. Hi, I'm Alex. I am one of Winning's students. And today I'm going to talk to you about correlations between time series. So really exciting topic. Actually, I'm going to try to convince you that it is a little bit exciting. So whether it's exciting or not, oftentimes in field disciplines where we go out into the field, go out into the world and take measurements, we often find ourselves taking correlations between time series. It turns out that evaluating the statistical significance of these correlations is a surprisingly difficult task. And because of this, existing tests that we currently have a variety of downsides. For instance, they may be limited to only linear forms of correlation. They may make strong assumptions about your data. They may lack theoretical guarantees, or they might have like a parameter and you got to pick the right parameter. And if you don't get it right, then it's not a legit test anymore. So that one's kind of unfortunate. And a lot of tests have more than one of these downsides. So I'm going to describe a new test. I'm going to call it the truncated time shift test. That's going to avoid these problems. And hopefully we'll have time to do a fun little demo with a time series from a previously published long-term human microbiome study. Okay, so researchers often look for correlations or look for meaningful relationships between time series. So for instance, between grassland productivity and rainfall, between microbial abundance and temperature, or perhaps inspired by Tom Bell's talk yesterday, between different species in a tree hole. But not all correlations are meaningful, right? So for instance, here is a time series of the monthly opening price of the S&P 500. So it's an index to indicate, it's sort of a general index for the stock market. And here's the distance between Saturn and the sun over the same time period. And so these two variables have nothing meaningful that relates them. But if I put up their joint plot and take their correlation, you know, I'm not going to compute it, but it's visually a very strong correlation. So you know, not all correlations are meaningful. When is a correlation meaningful? And I claim a correlation is meaningful when it indicates dependence. So what is dependence and why does it matter? So throughout this talk, we're going to start with the simple case, and then we're going to ramp up in complexity to try to get everyone on board. So simple first. Two dice, X and Y, are called independent if the chance that I roll a 5 in X and a 2 in Y is the same as the product of the chance that I roll a 5 in X and a 2 in Y. Oh, I can point, cool. And so you know, there's nothing magic about 5 and 2. The equation must hold if we substitute 5 and 2 with any pair of dice rolls, right? Otherwise, they're dependent. Okay, so now more complicated temporal processes, time series. Two temporal processes, X and Y, are called independent if the chance that X has a trajectory that looks like this and Y has a trajectory that looks like that is the same as the product of the chance that X looks like this and Y looks like that. Again, nothing magic about this and that. It has to hold for any possible pair of trajectories that I could come up with. So why does dependence matter? I'll make a claim now and then I'll talk a little bit about it. So I claim if X and Y are dependent, then one of three things is true. Either X causes Y causes X, or something else causes both. And this is known as the common cause principle, often attributed to Hans Reichenbach. So I can't prove this from math. This is sort of a way that we think about the world around us intuitively, but I've kind of spelled it out here. And it's also often thought of as a cornerstone of the modern statistical theory of causality. Okay, so then how do we test whether our time series are dependent? We have this fancy new word now, right? So again, starting simple and then ramping up, right? So imagine I have a test tube. This is just thought experiment. These aren't real data. And I'm growing bacteria and I'm growing yeast in this test tube. And I want to know, are they dependent? Well, I can take their Pearson correlation coefficient. And I see this very impressive 0.98. Okay, great. But does that indicate dependence? Well, if I have a second test tube, I can do a comparison. I can now take the correlation between the bacteria from trial 1 and the yeast from trial 2. And that might look like this, okay? And so this will be my null model in some sense because I know that these two are independent because I did them that way. And so, you know, in fact, if I have a lot of test tubes, I can correlate the bacteria from trial 1 to the yeast from trial a lot of other things, and that's plotted here, and you can read it off here if you want. And so I end up with a bunch of these null correlations. I can develop a simple test from this scenario. I'm going to call it trial swapping. So the first thing I'll do is I'll count up the number of null correlations. I'll call them n null, And then I'll draw a horizontal line at my original correlation and count the number of null correlations on or above the line. I'm going to call that n bigger. And then I can write down my p-value. N bigger plus 1 over n null plus 1. The plus 1 just comes from my original correlation. That's why it's colored pink. So this test has a really nice property, and that's that it's exactly valid. So what do I mean by that? I'm going to use this word a lot, so I'm going to define it for you now. If we infer dependence only when p is less than some significance level alpha, often we choose alpha 5%, then our false positive rate will be at most 5%. So valid tests allow us to cap the false positive rate of our inferences. So that's kind of nice. Okay, so that was wonderful, but often we only have one trial. So maybe we only have one biogas plant in Leeds, or we only have one Earth whose climate we're measuring. And I call this the N of 1 problem. And so how do we deal with the N of 1 problem? So there's various ways, but there's two that are particularly popular as far as I can tell in ecology and environmental science. So one is linear tests, and these are going to be parametric. And these are only going to work for linear correlations because they rely on an analytical derivation. And they usually rely on a modified z-test or t-test, and we've modified it to incorporate the fact that this is a time series. And this is one of these tests where I put in a little fudge factor, and I got to get the parameter right. So that's a little bit of a bummer. So another way of addressing the N of 1 problem is to use surrogate data tests, and these are non-parametric. And these will work for linear or nonlinear correlations, and they typically rely on computer simulations. So by the way, just as a quick aside, when might we want to use nonlinear correlations? Well, we've seen a couple relationships throughout the past week where something kind of goes up and then it kind of comes down, right? So Pearson correlation, this linear correlation, won't have an easy time seeing this. It'll be close to 0. And then if we use a measure of nonlinear correlation, such as mutual information, it will sort of reproducibly be greater than 0. So when we have sort of important nonlinear structure in the data, that would be difficult to capture through linear methods. By the way, if someone says, oh, this is the prediction accuracy using machine learning, usually but not always, that's a form of nonlinear correlation. Okay, so for that reason, we're going to focus on these surrogate data tests for the rest of the talk. We can totally talk about linear tests later, but for this talk, surrogate data. So how does this approach work? These surrogate data tests, how do they try to solve this impossible N of 1 problem? Well, we start, as one would, with two time series, x and y, and we throw them through our correlation function. And for me, and for right now, a correlation is any function that takes in two time series and spits out a number. So very, very general idea of what is a correlation. Next, we'll replace y with a surrogate, and this is going to come from your computer simulation. And then we'll just run it through the same process. So we didn't change x, but we did swap out y. And this will be our null correlation. And we'll do this a lot of times, and then we'll use the same formula that I've quoted before. P is n bigger plus 1 over n null plus 1, where n bigger is the number of surrogate correlations stronger than or as strong as the original, and n null is the total number of surrogates. So when is this p-value valid? Well, it's written down here in fancy language, but basically it's when our simulations are doing a good job of simulating the trial swapping process, when these surrogates are good stand-ins for independent trials. Okay, well that's fine, but then like how do you do it, right? How do you actually make these surrogate time series? And so there's a bunch of methods available, and they all have some condition under which they give you a valid test. So one thing you can do is you can fit a model to y and then run the model. And this, I think, would be valid when your model is correct. Here, I think it's a pretty high bar because your model not only has to capture like the general scientific idea of what's going on, but actually like pretty faithfully reproduce the statistical property. So this is a little bit difficult. You can try to randomly shift the Fourier components of y to generate your surrogates. This is often described as being appropriate for when y is a linear, stationary, and Gaussian process. You can randomly shuffle the time points, and this is valid when y is not really a time series, but it's actually IID. Please don't do this. This happens way more often than it should, and so like please let your friends know. Don't do this one, please. But it's unfortunately very common. You can try concatenating random blocks of y, and it's not really clear. This is kind of a heuristic, but maybe it would be valid if the blocks are independent. And so these all seem really restrictive. It's not really, they seem like they're asking for quite a lot. So another thing we might think of doing is shifting y in time. And so I don't really know when that's valid. Okay, well, anyway, do these work? Let's look at some simulation examples. Well, I guess the answer is no. But anyway, let's go through it anyway. So I'm going to simulate two independent time series from a variety of ground truth systems. And here they are. I can't really go through them, but you know, they kind of have very different visual appearances, and I promise you that their mathematical properties are kind of diverse as well. And so we're going to do the boring thing, test for dependence at the 5% significance level using Pearson correlation. And so here I'm plotting the false positive rate, and green is good because it means you're at or below 5%, and then other colors are like less good. And so right, so like if we went back to the definition of valid, right, if you were at 5%, then that suggests that you're a valid test. Okay, great. So immediately all tests have too many false positives in at least one system. Sorry, the rows are the different ground truth models, and then the columns are the different tests. These have fancy names because I'm using the real deal names, but they come from the same ideas as I had in the table. So all tests have too many false positives in at least one system. But the time shift test is coming closest to a perfect game. So maybe we can tweak it to make it actually perfect. So let's go do that. So in order to do that, we need to know what it is. So the first thing we do for this time shift test is that we truncate our X sequence. So we pick a number R, and we can talk about how to pick R, but I don't have time to right now. And we throw away R data points to the left and R data points to the right, and we focus on the middle. And I'll call that X trunk. We do the same thing for Y, and I'll call it Y trunk, except that Y trunk gets to kind of slide around. Y trunk of delta gets to slide around. And so when delta equals 0, that's our original time series for Y. And then when delta is not 0, those are our surrogates. That's kind of the idea here. So next, you do the next thing is you take the correlations at each value of delta as you slide it around. And then we're going to have to pick do the thing that we did again with the n bigger. So we're going to count something. N bigger is the number of, now in this case, shifted correlations that are at least as large as the unshifted correlation. And so I'll recolor everything again, right? So this is delta equals 0. So this is our original correlation. And then I see 4 of the surrogates that are bigger. So in this case, n bigger equals 4. I just picked this example so that I could zoom in on the ones that were above. But in general, you could have spikes over here. There's nothing magic. Okay, so then if we compute the p-value using the standard approach, n bigger plus 1 over n null plus 1, n null reduces to 2r because there's 2r to the left and right. You know, is this valid? And so the condition again was that the surrogate needs to be drawn from an independent identically distributed replicate of the original process. We don't have time to do like the question answer thing, but basically the answer is no. And what got missed was independent. So this condition gets violated, and you can see that because like two surrogates that are right next to each other in shift space are going to have almost all the same data points. So they're not going to be independent. So we lost this independence condition. But it turns out that we can correct for this problem. And the way we do it, and I wish I had time to like give some intuition, but I don't, is we write down this other p-value, and I'm just going to call it u in this case to distinguish it from, I already wrote down p, and I just get rid of this 2 here. That's what I did. And basically what we're doing is we're making the test a little more conservative to correct for the fact that the surrogates are no longer independent. That's kind of what's happening. If you want the proof, it's on bioRxiv. I'll have a QR code later. Okay, so I'm going to call this procedure the truncated time shift test, which I foreshadowed earlier. And the mathematical result is that the TTS test is exactly valid. So again, if we assume y is stationary, then if we detect dependence when u is less than alpha, then our false positive rate will be capped at alpha. Okay, wonderful. I mentioned this condition here. Let's just mention like what is stationarity? What does this condition mean? So I'll do a quick detour. What does it mean to be stationary? Well, when we have a time series, in statistics, we often think of it coming from a random time series process. And so you might have observed this one, but you could have observed that if you kind of replayed the tape of whatever. And maybe it could have been this, or it could have been one of these, so that at each time point, you have a distribution of possible values. And to be stationary, it must be the case that if you look at any other time point, it's the same distribution. Actually, the condition is a little bit stronger. To be really stationary, I have to be able to look at 2 consecutive time points that are here and maybe some at any other place, and these things have to be the same. Actually, it's a little bit stronger than that, and this is the last one. So this is actually the real definition, is that if I look at any n consecutive time points, like over here and then over here, I can't draw the histograms for you, but you have to imagine them, that these would have to be the same. So this last condition, which of course subsumes these other 2, is the definition of statistical stationarity. Great. So what kinds of systems would satisfy this condition? Systems at equilibrium. So for instance, a population that's kind of sitting at carrying capacity. Periodic systems are often stationary. Chaotic systems are often stationary, and Markov systems are often stationary. Okay. You know, yeast exponentially growing in a test tube would not be stationary. So now we have our condition, and we can slot the time shift test in here, and the validity condition is that y is stationary. Wonderful. So this is a much more general condition than the others, because these also require stationarity, and then this one needs a model. So we can go back to this benchmark thing. I've highlighted the new version of the TTS here. We've got a perfect game. Wonderful, right? So our simulations agree with the math. That's great. I can also add in some non-stationary time series, like a classic random walk or an AR1 with an additive trend. And you know, it's cool. We're also getting a perfect game with them too. In general, you can't do this, but for at least these classic examples, you can. So that's kind of nice. We have a little bit of robustness against assumptions. And then, you know, the beauty of these surrogate techniques is that we can go in and use them with non-linear correlation methods, and they'll also work. Okay, great. One last comment before we go to the data. No free lunch. The TTS test does require more data to detect a real dependence, right? So if I have these 2 time series here that are coupled because they have a shared noise term, then you know, here's the true positive rate, the rate at which we actually detect this very real coupling between them. You know, the TTS test is kind of at the bottom. I need more data before it's going to do as well as other tests. So that's the price for having like this very rigorous test that has fewer assumptions. No free lunch. So that's how it is. Okay, so an example. We know that different what? Oh no, why? I'm so sorry. That's very unfortunate. Okay. Okay, sorry. Yeah, that's it. Okay. Oh, did something bad happen?
Yeah, it was, yeah. Ooh.
Oh, okay. Well, oh, is that the Zoom is seeing here? I see. Oh, oh,
That's okay.
Okay. I will wait. I'll be patient.
There we go.
Okay, thank you very much. So we know that different sites on the human body host different communities of microbes. And so it's very difficult to test for dependence within a site, because as people have mentioned, right, what you'd really want to have is sort of the absolute biomass values. But very often, unfortunately too often, these are not observed, and often we really observe these proportional abundances. And so obviously, where you divide by the total. And so these are trivially dependent, even if these are not, right? And so you have to worry about spurious correlations, and there's efforts to try to deal with this, but I think that's beyond the scope of what I'm doing in trying to deploy this new technique. Instead, we can test for dependence between body sites. So for instance, if this is the skin and this is the mouth, if these are dependent, then these are too. Okay, so we're going to go ahead and see if we can find dependence between the communities at different environmental sites on a human body. And Caparasso et al. Did sample a human body for over a year, once every day, kind of with some gaps. So that's a really cool data set to try and deploy this test on. And so they sampled at the tongue, the left palm, the right palm, and the gut, which is really the poop. But can we detect dependence between these communities, right? And so in order to do that, I need my correlation function. How do I define a correlation between two body sites? I'll just throw one up here. So for instance, if I have my two sites, I'm going to start by counting off their shared microbes after they've passed some quality control test. And I'm going to look at the relative abundance of this microbe on the palm and in the mouth, and I'll just take their correlation, and I'll call that row, the orange row, and then I'll do it for all of them. And then the correlation between two sites will just be the median of these. And so this statistic has the nice property that it kind of has this plain language interpretation of an inter-site correlation for like your typical species. But also, I don't know how to do a parametric test with this median thing. So I would need to use some kind of surrogate data test here, I think. So I'm going to go ahead and do that. I'm going to use the TTS test, and I end up seeing dependence between the two palms, as you would expect. Sorry, these numbers are the correlation values, and I'm drawing an arrow if I see dependence at the 5% level after FDR adjustment. But also between the palms and the tongue. So I mean, I can't be sure of anything, but this would be suggestive. This would be consistent with a model in which there is fast migration among these sites on like daily timescales that is significant enough that I can pick it up here and be kind of slam dunk sure because I have this really, really conservative test. Caparasso et al. Used a much less conservative, well, not kind of. They used a parametric test, so the paper that published the data, and they didn't actually account for the fact that it was time series. So it was even maybe a little bit of a sketchy statistic, but they didn't find these other links. And the reason for that, I think, is that before they correlated two time series, they compressed their data into a single number to represent the left palm, a single number to represent the tongue. And so it's more difficult to see these more granular details because they're limited to these more rudimentary statistics using parametric tests. Okay. Summary. Testing whether two time series are independent is a common research task made challenging by what I call the N of 1 problem when we only have one time series. Tests suffer all these problems, and so the TTS test avoids them. Of course, no free lunch. It is more conservative, but this radical flexibility allows us to use boutique correlation metrics with much greater certainty. I have to thank a lot of people who have made great contributions to both my understanding of math and connecting it to things that matter. There's a lot of other stuff that I haven't had time to talk about. We have a preprint on bioRxiv where we get super nonlinear. We go into some other really fun examples, and we just go into much more detail on how the test works and when it might not. Yeah, that's it. Thanks for listening.
Well, thank you, Alex. That was fascinating. Also a little bit disturbing because I'm doing some time series correlations and I now realize I've done them all wrong. So I may come to talk to you about that. But yeah, so do we have a couple of questions? Caroline?
Very interesting. But I wanted to ask, so do you have a test to check how long the time series has to be for the TTS to opt from the other methods since it needs a long time series to be useful? So no, I guarantee you the TTS will not outperform. Well, so it's kind of yes and no, right? So if we go back to that chart where we saw the power, which I already went too far for, it always underperforms in the true positive rate. So at every single time series length, it will always be worse, but for the false positive rate, it has a guarantee, and none of the other methods do. Okay, and then maybe the accuracy. I mean, both what's positive and true positive. I mean, the mixture.
The accuracy. So that is interesting. You can't. So if you want to maximize accuracy, and that's all you care about, then don't do hypothesis testing. Hypothesis testing is really useful when you want to be totally sure that you've capped your false positive rate.
And I had another question. I didn't really understand how you could get compositionality by comparing between body size.
Okay. So, basically the idea over here is that the compositionality is going to trivially make these dependent on each other and trivially make these two dependent on each other, but it won't make this dependent on this. And if you want to see the details, I have a proof in the bioRxiv paper where there's the, the measure space, and there's like some theorems and stuff. And so yeah, you are totally allowed to compare between two sites if the compositionality is only within a single site. Right. So the biological meaning is kind of like at least one microbe is migrating from here to here, but I can't necessarily tell you which. So you're totally right. It's a very, very weak result that you're getting, but at least it's not a trivial dependence.
Okay, we had, actually you were next.
I wonder if you could say a little more about something you mentioned earlier on, which would be the role of causality and I guess also locality here, because to me, one interpretation of the fact that you need the stationarity is that a stationary process has no arrow of time anymore. So therefore, when you shift in time, there's no concept of causality with something that has no arrow of time. And so I wonder if in some of these other cases, if you know something about that, because like the problem with comparing two things at every instant in time is you're assuming basically an instantaneous transmission of effects of things, whereas of course real systems is always some delay, whether that's faster or shorter than the time scale of sampling. Anyway, I'm wondering like what role you think this plays in there, and could we use that if we know something about that in terms of biological systems? Can we use that to better inform how we would implement?
Yes, the short answer is yes. The long answer is so basically one challenge that appears in what I've just told you is that I'm essentially saying I'm taking the cross correlation between two time series and asking, is there a peak at zero? That's basically what I did. And so if you have a delay, I will not see it. I will actually think that there is no correlation between the two time series if one time series is correlated with a delay to the other, because the zero correlation will be lower than all the delayed correlations. So that's a big problem, and you can fix it by pre-shifting one of the time series if you know how much to pre-shift it. If you don't know, then you can try a bunch of them and do a Bonferroni correction. So those are all in the preprint. But to your point about the causation and getting a little bit more fundamental or philosophical, for me, dependence between two time series just means that like some random variable at some point in time is related in a causal sense, in the sense that I described earlier, to some random variable in some point in time here. And so I actually don't know which of those, but at the same time, I'm able to like learn that at least something's going on without having to pick which one I'm looking for.
Okay. All right, quickly, Orkun.
Thanks, brilliant talk. If we go back to the spurious correlation example.
Yeah.
Will any of these methods, including yours, tell something different about that, or will they all say that those data sets are correlated?
So my method will probably say it does not. There is actually yeah, probably will say no correlation, but not because it's correct, just because of an artifact. In general, all these methods require stationarity, and having time series that are non-stationary, trying to correlate them using any method is basically impossible. I can't remember the precise mathematical statement, but if you don't know any kind of regularity condition, such as stationarity, then it is a non-identifiable problem.
All right, well, on that note, let's thank all this morning's speakers.
Okay.
Yeah, quite a few questions for actually. Probably on the thing that you don't talk about, which, we're very